Chapter 7 on geometrical optics consists of 3 subtopics. The first subtopic is on spherical mirrors, where you learn how light reflected off a curved mirror, be it a concave mirror or a convex mirror. So you learn that you can use ray diagram to determine the characteristics of the image. You can also use the two formulas to find out the relationship between the object, the image, and the mirror itself. You learn about the sign convention, and you learn about the magnification, what value represents what characteristics. And then we move on to the second subtopic on spherical surface, where we learned how light, when it encounters a change of medium, what will happen to it. To be more specific, we learned that refraction occurs when there's a change of medium, and when the change of medium, we need to look at the index of refraction in order to know whether it will be refracted away or towards the normal. So the ray diagram is not part of your syllabus for spherical surface, it's only in your syllabus for mirrors, but you need to know that when it's a spherical surface, you have to know how to manage the situation, how to analyze the situation using the formula for spherical surface. So for spherical surface, you see that you'll be relating between object, image, and the radius of curvature, but this time there's a new component, new element, which is the refractive index. You also learn that the sign convention is quite similar to mirrors, and you use that to deduce the characteristics of the image produced either in one medium or another. So that's for spherical surface. Then lastly, you move on to the last subtopic for chapter 7, which is on thin lenses. So thin lenses is a build-up, or it's a continuation from a previous subtopic on spherical surfaces. To be more specific, why is it so? You may see that a lens is an object, is a tool which is transparent, allow light to pass through, but it consists of two refracting surfaces. So when you have light strikes on one surface, you get bent due to a change of medium, and when it escapes the lens, you experience another change of medium. Therefore, you undergo another refraction when it gets out from the lens. So there are many different shapes of lens which we will discuss later. Okay, the characteristics of lens is that it is usually made out of a material which has a higher refractive index than the surrounding. Usually, it's not always, but it's usually. Let's say you have a glass lens over here which is placed with air as its surrounding, and air will usually have a refractive index of 1, whereas the lens here will have made of glass maybe, then you'll be having a refractive index of 1.6, let's say. Okay, for any lens that you encounter in this chapter, lens, not mirror. For any lens, you notice that lens, the main difference compared to mirror is that it's transparent, allowing light to pass through. Okay, for mirror, it's reflecting off the mirror surface, so light cannot pass through. It's opaque for mirror, but it's transparent for lens. The second thing that you should know for lens is that it has two focal points, whereas for mirror, there's only one focal point. For lens, the two focal points are on both sides of the lens itself, and it lies on the optic axis that pass through the center of the lens, which you may see here. These black lines here represents the optic axis. Some books call it the principal axis. So your focal point will be lying on this principal axis or your optic axis. And one important characteristic of the focal point is that they should have the same focal length. Means by the distance of the focal point from the center of the lens should be equal for both focal points. If here to the center of the lens is 10 cm, then from the center of the lens to the second focal point should also be 10 cm. That's the characteristics of focal length, and it doesn't matter whether it's an asymmetrical kind of lens or a symmetrical kind of lens. Okay, so for mirror, you learn that focal length it's just half of the radius of curvature. For mirror, I'm saying for mirror, you learn that the radius of curvature is twice the focal length, because we always say focal length for mirror or focal point for mirror, it's the midpoint between the center of curvature and the vertex of the mirror. But I have to make a remark here. For thin lenses, this is not the case. For thin lenses, the focal length does still depend on the radius of curvature, but since now we have two surfaces here, you have to take two surfaces into account in determining the focal length. That's why the equation will be a bit more complicated than just r equals to 2f. Now you have two radius of curvature, and because there's a change in the medium, you have to consider the refractive index as well. So how do we relate the focal length and the radius of curvature? That we will use the lens maker equation, but that we leave it for the next few videos. Okay, so we have been saying that this is lenses, but I never really mentioned why do we have to specify that it's a thin lenses. Okay, it's a thin lenses due to some very technical reasons, but the idea is if you have a very thick lens, then the distortion is a bit too great that you cannot make approximation in your trigonometry and your geometrical derivation. Later you encounter the lens equation, you encounter the lens maker equation. All these equations here have some form of approximation in it, and the approximation will be broken down if your lens is too thick. Okay, we might touch on this why it is thin, this topic little by little throughout the next few videos, so you may get to know the idea better soon. Okay, so I'll go straight to the types of lenses. There are converging lenses and diverging lenses. Converge means by you focus onto one point, just like what you see here. The ray will coming in parallel to the principal axis or the optic axis, but they will focus onto one point. Focus, converge. Another type of lens, which we call it diverging lens, will be diverging out the light. You'll be spreading out the light instead of focusing the light. Just like what we see here, we see parallel rays, parallel with the optic axis, striking the concave lens, but you see that the ray refracted in a way that it will spread out with respect to this focal point over here. The ray is spreading out instead of focusing onto one point. Okay, so that's the main difference between converging and diverging lens. So let's try and identify the characteristics of the converging lens and diverging lens. For converging lens, or we call it positive lens, the center of the lens is thicker than the edge. Means by if you look at this lens over here, we call the center this middle portion of the lens. We call the edge of the lens the top and the bottom portion of the lens. So I think it's quite clear here. It's slightly exaggerated, the drawing here, but you can see that the center portion is much more thicker compared to the top and the bottom, the edge. So in this case, this lens here is qualified to be called a converging lens. This is also the same. It's thinner at the top or bottom, but it's thicker at the center. Same as this lens as well, thicker at the center. So for this kind of lens, we call it converging lens or positive lens. Okay, but for our syllabus, right, our syllabus usually generalize everything and call these kind of lenses convex lenses. Okay, convex lenses, it depends on how you use the word. It can be a bit ambiguous whether this should be called convex or you should be called planar convex or something. But I think for your syllabus, you call all these kind of all these families of lenses to be convex lenses. Okay, so for what do you know about converging lenses is they share positive focal length. So if you see a converging lens, when the light is being focused by that lens, then it's a positive lens. Then the positive focal, then you get positive focal length. So f should be a positive value. Okay, so for converging lens, right, if you vary the distance of the object away from the lens and you try to determine the characteristics of the image form, you'll notice that there's a strong similarities between the characteristics of image formed by the converging lens and the concave mirror. The concave mirror and the converging lens, or the convex lens, or the positive lens, they share quite similar properties of or characteristics of image form. Okay, we'll investigate that later. Okay, so here are two general ways of how we usually represent converging lens or convex lens. So converging lens, we see that if we have rays striking on the lens parallel to the optic axis, you see that those rays will be refracted towards a focal point over here. Whereas the opposite case is if there's light traveling in a direction diverging out from the focal point, emerging from the focal point, and it strikes the lens, you see that the refracted ray will now be parallel to the optic axis. You can think of these two here as mirror image to each other. It's just that the one is from parallel to converge, one is from emerging to parallel. They are just mirror image of each other. So this is how we usually represent converging lenses or convex lenses. Okay, moving on to diverging lenses. Diverging lenses, you see that the center portion, which is the middle portion over here, will be thinner than the edge. You can see that the top and bottom portion here are quite thick, whereas the center portion is quite thin. The same for this lens and this lens as well. All three of them has quite a thin waist, and they have a big head and big top and bottom. Okay, so we call this kind of lens a diverging lens or negative lens or concave lenses. We say it's diverging again is because it's diverging out the light that pass through the lens. Okay, so since we call diverging lens as negative lens, it's immediately known that the focal length should be negative. The negative here, this negative here is why we call diverging lens negative lens. Okay, and for diverging lens, we also call these families of lenses to be concave lenses in your syllabus. Okay, some might debate that this might be called planar concave or this one will be biconcave. But for our syllabus, we call all these kind of lenses to be concave lenses. Then for this kind specific, we give it a name, we give this a name, we give this a name later. But the whole family, we call it concave lenses. Okay, the image formed by the concave lenses, if you compare it, it'll be quite similar to the image produced by a convex mirror. Okay, it means by if I put an object near the concave lens here, then I vary the distance of the object with the lens, you see that the characteristics of the image form will be quite similar to the characteristics of the image form for a convex mirror. Okay, later I will move on to talk about the image characteristics, and you may try to compare it with convex mirror. Okay, again you see that parallel rays come in and diverge from a focal point which is in front of the lens. Whereas if you have light rays trying to converge towards a point behind the lens, you see that you get refracted to be parallel to the optic axis. Okay, so these are characteristics of converging lenses and diverging lenses, also known as the convex lenses and concave lenses.